Good evening, everybody. It's Friday, May 1st, and this is Nighttime Mathematics Radio. Show always has the same format. You ask your questions on Twitter, and I try to answer them live here on the air. We've actually got a full slate of questions tonight, so there's no real need to wait the usual minute to see if anybody wants to tweet in. So let's get right on started with the show. So we had a couple of questions came off of Twitter, asking questions about linear approximation and about Newton's methods. Let's take a look. I actually have them printed out here and right on the notepad, so we don't have the usual pain of trying to read my handwriting. But the first question asks, given the function below, use an appropriate linear approximation, it says, to estimate g of 1.9. Simplify and write your answer in decimal form. It asks for 1.9, and the reason it becomes obvious when you look at this function, and the reason it's g of 2, which is really close to 1.9, is actually easy to figure out. Because that's 5 times e to the... This is 3x minus 6, so that's e to the 0, minus 9 times the natural logarithm of 2 times 2 is 4 minus 3 is 1. Normally the log in the exponent would be kind of messy. We'd have to use a calculator or try to figure out what we're doing, but e to the 0 and log of 1 I can do without a calculator. E to the 0 is 1, log of 1 is 0, so g of 2 is just equal to 5. So now we're asking for g of 1.9. And the question is, how do we get that? The answer is we use a trick, essentially. We say, well, g of 1.9 is about equal to g of 2 plus the first derivative. We basically, the first derivative, g prime of 2, times how far off of that known point we are and in what direction. The answer is we are off by 0.1 in the negative direction. And this should look really familiar. This is just the equation of a line. Here we've got the slope. Here we've got the intercept, and we're looking, it's the intercept if you imagine having a function which is how far off of the known point are you. So when you're 0 off of the known point, you're just at g of 2. And as you move off of it in either direction, you multiply how far off you are by the slope. Well, g of 2 we know, that's 5. How about g prime of 2? Well, now we actually have to figure out this derivative. Well, g prime of x, and now we just have to use the chain rule really a lot. Because the derivative of 5e to the 3x plus 6 is 5e to the 3x plus 6 times the derivative of the exponent, because that's chain rule, which is 3. Minus 9 over 2x plus 3, minus 3 rather, because remember, the derivative of natural logarithm is 1 over x. Except then times again the derivative of the composed function, which is 2. So that's equal to 15e to the 3x plus 6 minus 18 over 2x minus 3. Now, just like last time, when we plug in 2, g prime of 2 is equal to 15 times, well, e to the 1 again, because again, oops, that was minus 6, I'm sorry. That makes more sense. That doesn't change anything we did before, because the derivative of minus 6 in the chain rule is the same as the derivative of plus 6 in the chain rule. It's 0 both ways. So it's 15, Now minus 18 over 1. So in other words, it's minus 3. So what is g prime? What's g of 1.9? Well, it's about equal to 5 minus 3 times minus 0.1. So 5 minus, so plus 0.3. So it's about equal to 5.3. And now you might wonder, well, how far off are we? How good is this? Well, I've got a calculator right here. Let's see how close this is. Actually, let's do something even cooler. Let's look at let's switch to the grapher real fast. And let me switch to the grapher. Now first, we change this function so we're plotting the actual function that we're interested in here. Y is equal to 5e to the 3x minus 6 minus 9 times the natural log of 2x minus 3. Oof. We got to zoom in a little bit there because you see it peaks sharply right around 5. You can see it hitting 2 right at 5 like we said. Let's zoom in right around that point. So let me zoom in right here so we can see better what we're doing. So you go through 2 right there. Now what is it when we go back to, this is 1.6, 1.7, 1.8, 1.9. The actual answer is up here. So it is 5 point something, but it looks like it's more like 5.7. Why is that? What happened? Well, the thing you can see is the slope is increasing sharply here. So this approximation is okay. I mean, it's bigger. It's between 5 and 6. It's bigger than 5, so that much is right. But our approximation here is the tangent line. So let's write down the tangent line so we can see what that looks like. Our tangent line says y is equal to 5 times... Sorry, 5 plus, because 5 was the value at the point, minus 3, which is the slope there, times the x value, times, not the x value, but how far off of 2 you are. And I can simplify the algebra a little bit here. I'd say plus minus, that's sort of horrible. I can turn that into, if it'll let me do it, I can turn that into 5 minus 3 times x minus 2. And what we see is, it's the tangent line right there. And so it really does go through 5.3, just like we said. And it's approximate, because the actual function changes. The actual function isn't a line. How good is it? Well, the closer in we are, the better it is. 0.1 off is far enough off that it's off now by about 0.3 or 0.4. But the closer in you get, the better this approximation is. And that's the whole idea of a linear approximation. So that's that first problem. It's close. It's not great, but it's close. The second one is something called Newton's method. And this is a way of trying to find the zero of a function, or in this case, the value where a function goes through a point. So we're interested in saying, well, there's one point where on the curve, y is equal to 3x to the 4th plus 4x cubed, where the slope of the tangent line at the point is equal to 36. So we actually are interested in y prime. 12x cubed plus 12x squared. And we'd like to know where is this 36. So the equation we want to solve is 12x cubed plus 12x squared equals 36. And the point they say to start with is x1 equals 1. Well, if we plug in 1, what do we get? We get y prime of 1 is equal to 12 plus 12 is 24. So there's an interesting starting point. So the idea of Newton's method is you keep using linear approximations and solving the equation you're trying to solve not for the actual function, but for the linear approximation at that point. What's the linear approximation of 12x cubed plus 12x squared? Well, at 1, it's y of x, this is our approximation function, I should say, is about equal to 24 plus, this is y prime. Y prime of x is about plus, and now we need the second derivative here because, of course, we're looking, this is the derivative of the derivative we're interested in here. Double prime of 1 times x minus 1. Right? This is what happens around 1. Well, what is y double prime? Well, we can figure that out quickly enough. Y double prime is equal to 36x squared plus 24x. So y double prime of 1 is equal to 36 plus 24, which is just 60. So it's about equal to 24 plus 60 times x minus 1. And we want to know, when is that 36? So we can solve. 60 times x minus 1 is equal to 12, or x minus 1 is equal to 12 over 60, or 1/5. So x is equal to 6/5. And that's our x2. How close are we? Well, what's y prime of 6/5? It's, and at this point it's probably worth using a calculator. It says you're allowed to use technology for basic arithmetic only, so that's fine. I've got a calculator here for some basic arithmetic only. So 6/5 is 1.2. What I want to know is, what's 12 times this cubed, so times 1.2 times 1.2. Oops, clear. The danger of trying to use a calculator blind while not looking at it. 1.2 times 1.2 times 1.2 equals 1.728. So I want that times, what was it, 12. That's 20. Plus 12 times 1.2 squared. And there's now we're at 38.016. That's closer. We're trying to get to 36. So we've already gotten much closer. We've gone from 24 in the first guess to 38.016 in the second guess. How about y double prime? What's the slope at this point? Well, that's 36x squared plus 24, so that's, clear this out. 36 times 1.2 squared plus 24 times 1.2. Calculator should know order of operations properly to be able to do this. And it comes up with 80.64. So now we're trying to solve to get x2, which is what we've been asked to do. We've been asked to do 2 rounds of this. So we say y prime of x is about equal to 38.016 plus 80.64 times x minus 1.2. Oops. So we're just doing a second round of exactly the same method. The value is about equal to the value at 6/5, 38.016, plus the slope at that point times how far off of the test point you are. And we want that to be equal to 36, which is the point we're trying to find. Well, we can do that. So 80.64 times x minus 1.2 is equal to 36 minus 38.016. We can do that. Have to make sure this is under the light so you can see it. Okay, so that's minus 2.016. Divide that by 80.64. We get minus 0.025, so we're actually very close to the solution we're interested in here. So what we get here is that x minus 1.2 is equal to minus 0.025, or x is equal to 1.225. And that's our x2. Or x3 rather. So x3 is 1.225. So what's the value of the function there? Let's see how close we are. What is y prime of 1.225 as a finale? So that's 12. Let's get this under the light so you can see it. 12 times 1.225. And it should be that cubed. So cubed plus 12 times 1.225 squared. The answer now is 40, which makes me suspect I had a sign error somewhere. That seems very likely. Oh yeah, of course I did. This was a negative 0.225, so it's not 1.225. I made a quick sign error there. That should be 1.2 minus 0.25, 0.025. So that's, my test point shouldn't be 1.225, it's 1.2 minus 0.025, which is 1.175. So 1.175, quick sign error there. So what is 1.175? Same calculation I just did. Test it really fast. 12 times 1.175 cubed plus 12 times 1.175 squared equals... The answer is 36.03. So we've gotten very close, and that's our second round solution. This is the advantage of Newton's method. If you start kind of close to a solution, it converges very, very, very fast. Much, much faster than other methods. Is there a downside of Newton's method? Sure. If you start far from the solution, you may never get there. You have to start somewhere close to the thing you're looking for, or this may never work. And there's plenty of good examples where Newton's method will bounce back and forth between two bad solutions forever if you start too far away. This is Nighttime Mathematics Radio. We've got a few more questions after the break, but let's take a quick break to get our voice back and see what's going on. So I can chase the dog off of the microphone here. And after the break, I'll try some composed limit problems. This is Nighttime Mathematics Radio. Oh, welcome back to the show. Let's try to do some composed limit problems. Now, these problems work with a really strange function, so let me draw it out here. These questions say, well, let's look at a function that looks like this. It's defined between -5 and +4 inclusive. And between -5 and -1, it describes a semicircle. So we've got a semicircle over here. And then from -1 up to 4, or up to 2, it's just a straight line up to 2, 3, where it hits an open circle. So it doesn't actually take that value 2, 3, it just approaches it. Then it jumps down to 2, -1, which is a closed circle. It heads upwards to 1, 1. So the question, we're asked 3 questions here. For this very strange function with 3 weird pieces, we're asked first, what's the limit as x approaches 0 of f of x minus 1? Well, for this case, the composition is fairly straightforward. In this case, the limit as x approaches 0 of f of x minus 1 is exactly the same thing as the limit as x approaches 1, sorry, x approaches minus 1 of f of x. Right? You're just off by 1. This is just an offset. There's no real difference there. And fortunately, you can see the limit. Remember, to have a limit, 3 things have to happen. There has to be a limit from the left, there has to be a limit from the right, and they have to be equal. And if all 3 things are true, then that equal value is the limit. So what do we have here? Well, from the left, we're on the semicircle, and the limit at minus 1 is 0. From the right, we're on this line, and the limit from limit from the right is also at 0 at minus 1. They're the same, they're both 0, so that's just 0. And that's very easy. How about the second question? The question is, what's the limit as x approaches 0 of f of 2 minus x squared? Now this one's interesting, because here, we're approaching a point which does not normally have a limit. But that's okay. Why? Because the thing about 2 minus x squared is that 2 minus x squared is always, for all possible values, less than or equal to 2. And for everything that isn't 2, because remember, for a limit, we don't care about the point at the we don't care about the point at the point we're interested in. We're interested right at 0. So if you plug in 0, it's actually equal to 2. And everywhere else, it's less. We don't care about the fact that there's no value at 2. That doesn't have to happen for a limit. You can have a limit even if the function doesn't exist at all at a point. All we care about is that there's a limit on the side that we're looking at. In this case, we're looking entirely to the left. Because after all, this value can never be bigger than 2. So we don't care about this stuff. All we care about is this stuff over here. And for that stuff, the limit from the left clearly exists and is 3. So that's also well defined. Let's look at the third one. The third one says, what's the limit? This is a cool one. As x goes to 0 of the quantity, absolute value of x over x times f of x minus 1. So we're looking at this point. The question is, what is the absolute value of x over x? This is actually something you see all the time. It's a trick. At 0, it doesn't exist as a function. At 0, but we don't care. We're taking the limit as we go to 0. Everywhere else, it's just the sign. That is, if x is positive, this is a positive 1. And if x is negative, this is a negative 1. If it's 0, it doesn't exist, but we don't care, because that's where we're taking the limit. So what is f of x minus 1? Well, it's 0 from the left, and from the left, notice at this point we're approaching 0, so as we're approaching from the left, this will be negative 1, but it's approaching 0, so the function's approaching from underneath now, but we don't care, it's still 0. How about from the right? Well, on the right, this is a positive 1, and it's approaching down this line in the normal way, with no negation, so the limit is 0. And since it's 0 from both sides, and they agree, that's the limit. You notice here, if we were looking at almost any other point in this graph, except this one, that wouldn't work. If this was x minus anything other than this crossing point here, which I guess is 3, 0, this wouldn't work. Anywhere else, you wouldn't have a limit because you'd have the negative limit on the left and the positive limit on the right, and they wouldn't agree, so you wouldn't have a limit from both, a two-sided limit like this. But at this one point, well, I guess at this one point and also at this other one point over here, that doesn't hurt us, and the limit is still 0. And this is Nighttime Mathematics Radio. Well, everybody, that's all the time we have for tonight's show. Keep tweeting the questions in. We'll come back Monday night, answer any questions people may have. So for the moment, in this strange world where the homework goes on and on and on, but the classes have all stopped, except for some mysterious Zoom meetings, keep tweeting the questions. I'll keep trying to answer them late weeknights. Good night, everybody. Stay safe.